Hello friends, in this video we're going to talk about the Boltzmann distribution. Now, what is the Boltzmann distribution? The Boltzmann distribution is based on a statistical representation of states of a particular thermodynamic system at a given temperature developed by Ludwig Boltzmann back in the 19th century. Now, we're not going to spend too much time on the history here. We'll talk about that a little bit later. We're just going to spend time on the Boltzmann distribution, which is an outgrowth of the statistical analysis of states of particles, molecules, atoms, etc. at a given temperature, T. So first of all, one thing to note is that the Boltzmann distribution represents a distribution of particles in a particular energy level as a function of temperature and corresponds to an equilibrium. So that's actually the key here when we talk about this. We are talking about an equilibrium state. If we're not in an equilibrium state, then all bets are off in this situation. And in fact, what you should know about temperature is that when we talk about temperatures of systems, those temperatures correspond to the assumption that the particles in a particular system are in equilibrium, and their energy distribution corresponds to an equilibrium energy distribution. So that's what we're talking about here, is an equilibrium energy distribution. And the Boltzmann equation allows us to determine the relative number of particles in particular energy levels, all right, and this is a quantum. Of course, when we talk about energy levels, we're talking about the quantum mechanics of the system in these energy levels, but it represents a distribution of molecules in various energy levels as a function of temperature in kelvins. And again, one of the things you should always assume is that when we talk about temperatures, unless told otherwise, assume that we're talking about kelvins. All right. So what is the equation for the Boltzmann distribution? Well, if I have two energy levels, which I will represent here very generally as energy level J and energy level I, the ratio of particles in energy level J to energy level I is equal to the ratio of degeneracies, and we'll talk a little bit more about that in a couple of minutes. G sub j representing the degeneracy of level J, and G sub I representing the degeneracy of level I, times a term here where we have the natural number E, and we're raising that to a power which depends on the energy difference between level J and level I, and we're dividing that in that power by the product of K, which is the Boltzmann constant, times T, and again T is in Kelvin. K, the Boltzmann constant, with 3 sig figs is 1.38 times 10 to the minus 23, and the units are joules per Kelvin. All right, so that's what we've got here. So again, N sub j represents the number of molecules or particles in level J, all right, at energy E sub j. And N sub I, of course, represents the number in level I with energy E sub I. All right, so that's what we've got there. Now, what's this degeneracy thing that we're talking about? The degeneracy represents a number of states, and this will probably become a little bit more understandable later on when we look at specific systems. And we see that we've got this particular property. The degeneracy corresponds to the number of states which have the same energy. All right. All right, and so, and again, that's referred to as degeneracy. All right, so that's what we mean when we talk about degeneracy. We are talking about the number, and again, we'll look at some specific examples of that, and we'll see how we can have multiple states which have the same energy in these situations, and vibrations would be one of those, which we might talk a little bit about in a few minutes. And then we'll look at some specific examples and what that means a little bit later on. So this is our Boltzmann distribution. What we'll note is that specifically, if as the energy difference increases, for example, if level J is higher in energy than level I, what we'll note is that as the energy goes up, then the number of molecules drops. And that should make sense. I mean, if you're going to higher energy, the population of molecules in the higher energy states will be lower as you go to higher energy, assuming no degeneracy. Degeneracy throws a little bit of a monkey wrench into that, and we'll see some examples later on, but we're going to stay away from that right now to avoid confusion. So again, in general, when we look at these systems, what we're going to note is that we see kind of in a situation where the degeneracies are the same, all right? So if we've got a situation where the system is either non-degenerate, meaning that's only one, all right, or we have a situation where the degeneracy of G sub I is equal to G sub J, then of course the ratio is equal to 1, and that makes life much easier in a situation like that. Let me just make that a little bit clearer. So that's going to be equal to 1 in that situation, all right? And then our equation in that situation where the degeneracies are the same for the two energy levels, it simplifies the equation a little bit because we get rid of that pre-exponential term. And I'm just going to write this as delta E, where delta E is the difference in energy between the two, divided by KT. All right. And so if you've got a relationship like that, what we're going to note is it's a very simple relationship that we have. If we've got E sub J is greater than E sub I, that simply means that the energy difference is greater than 0. All right. And so in a situation like that, when we have that particular situation, that means that if we were to plot this ratio, and let's just assume that we're plotting it relative to the lowest energy level. Okay, so what I'm going to say is that I want to know the ratio of molecules in an upper state relative to the very lowest energy level. It's just going to be a simple relationship here as we go to level as we do the energy levels. So as the energy levels, as we go up, as the energy levels increase in this direction, then we got a simple exponential, kind of looks like that, decay. All right. Now, and of course, you know that we've got energy levels, so it's actually not going to be continuous. It's going to be discrete when we talk about that, because they're going to be what quantum mechanics says about particles and their energy levels is that you have certain energies. That's why they're called energy levels. But there are some energies that systems can have and some energies they can't have. So when we talk about energy levels, we might be talking about something like this. Here's energy level 0, and here's energy level 1, and energy level 2, etc. All right. So as we go up in energy levels, all right, from 0 to 1 to 2, in this situation, the population of molecules decreases as we do that. Now, what's going to happen as we increase the temperature, though, is that if we increase temperature, so that as the temperature goes up, in those circumstances, what we're going to note is that we start to get more population of the upper levels. So, for example, if I was to do this plot at a higher temperature, let's call this one T1, and let's say T2 is greater than T1, and I plot it, what I'm going to see is something that looks more like that, which means that we're getting more population of molecules in the higher energy level. And that's actually fairly important because that affects properties, thermodynamic properties, for example, like heat capacity, does depend on the temperature. And as we increase the temperature, those properties do change, and the Boltzmann distribution is key for understanding that. Okay, so again, that's what the Boltzmann distribution tells us, is how that population distribution shifts as we go to higher levels. Now, I'm going to do a demonstration through Wolfram Mathematica, and later on we'll actually probably do some, I'll have you do some calculations with regard to this, but so here is a window, a Mathematica window, which shows us, I'm going to spread it out just a little bit so we can get a better idea here, and maybe actually let's increase the magnification of this a little bit so it's a little bit easier to read, perhaps. All right, so here we've got our situation for Boltzmann and temperature. And again, the temperature is actually crucial. We're going to find that, as I said, that temperature corresponds to an equilibrium situation, and temperature actually can be gauged by the Boltzmann distribution. The two are very much connected when we talk about temperature. So I'm going to scroll through this document real quickly here because we've already talked about some of these basic issues. Again, here is our basic equation, which shows the ratio of levels of molecules, of population molecules in particular levels, equal to the ratio of degeneracies, and then we've got our exponential term with the Boltzmann constant. All right, so I'm going to look at a specific example here, and an example where we actually have a graph where we can see the temperature dependence. And again, as I said, we'll actually do some specific calculations on this in a few minutes. But I want to show you graphically what this is telling us. All right, so we're going to talk about something called the harmonic oscillator. And again, this is something that we'll have a video on later when we get to discussions of vibrational energy and quantum mechanics. A harmonic oscillator is a good first approximation to vibrational motion in molecules. So, for example, when you do IR spectroscopy, we model that spectroscopy through the harmonic oscillator model, and you may have learned about Hooke's law in physics. Force is equal to negative k times x. Remember all that stuff from physics. Again, we'll be going into that in much greater detail in the future, but that's the harmonic oscillator. And we just consider for molecules and bonds of molecules, we treat them like springs that obey the simple harmonic oscillator laws. We do that quantum mechanically. And so when we do the quantum mechanical calculations associated with the harmonic oscillator, and again, I'm just going to give you the equation here for this. We'll talk about where that comes from at a later point. But right here, like you can see, I've got this equation for energy, where N here is an energy level. Okay, so here is the general equation for energy for the harmonic oscillator. Where omega in this equation is the wave number. You're familiar with, of course, when you run an IR spectrum, you actually get the wave numbers on the spectrum, tells you the position of different kinds of vibrations, like a stretching vibration or a bending vibration or something like that. You get wave numbers, and you may recall when we talk about wave numbers that wave numbers, and a lot of times you get a little, it's represented by a squiggly line, but a wave number is just the reciprocal of the wavelength of the photon that excites that vibration. Okay, so again, when you're running IR, you're getting the wave numbers, and again, we'll talk more about the quantum mechanics of that. This is the equation that we have here for the energy of level in wave number values. And then, of course, here is our Boltzmann distribution. Now, one of the things that we're going to note is that when we talk about these vibrations, and right now we're going to be talking about situations where the degeneracies of the two levels are the same, and that means that we've got this situation where the ratio is equal to 1 in this situation, all right, for the vibration. So this, in our simple calculation here, this ratio is going to be equal to 1. Now, the example we're going to be using is what's called the bending mode of carbon dioxide, okay? And the bending mode of carbon dioxide, actually, in the IR, is roughly 667 wave numbers. Okay, so we look at it's roughly 667 wave numbers. I know that when you've done IR spectra in organic chemistry, for example, you've not really looked down that to wave number values that low because it's a real mess in the so-called fingerprint region of the IR. But one of the things you do know, of course, is you do a background when you're running the IR. One of the reasons you run a background is to eliminate the contributions from molecules that are in the air, all right, and subtract those out. And one of those is carbon dioxide. So when you're running a background IR spectrum on an organic molecule that you may have done, you do that background. When you look at that background, you're going to see peaks due to water and carbon dioxide. And one of those down around 667 is a bending mode of carbon dioxide, which is more or less like a bird flapping its wings, like the molecule going like this. And I know you can't see my arms moving, but we'll be looking at some demonstrations of this a little bit later. The bending mode actually is interesting because it's that particular vibration that is a major contributor to global warming. The carbon dioxide in the atmosphere, that vibration absorbs a great deal of the infrared radiation that is released from the Earth, that's emitted from the Earth. And because it absorbs it, it prevents it from escaping the atmosphere. And that contributes to the warming of the atmosphere and hence the warming of the planet. Again, we'll talk about that a little bit later on. So in this case, then, we've got this situation where we're using the equation here for the population ratios, where the degeneracies are the same, so that's equal to 1. All right, and we have the situation where then, because that's equal to 1, we remove that term, and then I've just inserted the equation here, and we're replacing omega with 667 wave numbers in the calculation. And again, we'll actually do these calculations later on, just doing a demonstration here to show you. And we plot that, okay? All right, so I'm scrolling down here to this plot. Let me make it just a little bit bigger. It's going to let me do that. Maybe not at this point. I guess it's not going to let me do it right now. All right, so this shows a population distribution. The levels, level 0 represents the lowest energy level of the harmonic oscillator. And so this shows the relative population of level 0, level 1, level 2, etc. at 500 kelvins. All right, and so we see a general exponential shape. It's just that, of course, it's not continuous because we've got levels. We don't have a continuous range of energies available. We've got energy levels. Now, if we change that, what happens? And remember, we talked about what's going to happen is as we change the energy, if we increase the temperature, then we're going to start to see a shift in the population to higher levels. So if I change it from 500 to 1,000, for example, we'll see actually what's happened here, that you're actually beginning to see more molecules populating these upper states, 3, 4, and 5. We can go higher. And you're seeing again, you see the general shape is exponential, but you are seeing a greater population in the upper levels as we increase the temperature. And that's actually fairly important because as we start to populate the upper energy levels of molecules, and what that means is if you take the distribution of molecules, and say you have a mole, 6 times 10 to the 23rd molecules, then you've got, and you measure the energies of all the molecules there, then you're going to find this relative population distribution. So just estimating at this graph right here, so relative to energy level 0, okay, so at this particular temperature, then we would say that level 8, all right, and so we are talking about, something that's, as we scroll up, and let me go back to this energy level diagram here. So this showed 0, 1, 2. I'm going to actually kind of cut this and bring it down so I can keep going. So that when I do that, I've got energy level 3, 4, 5. I'm going to put these together, 6, 7, 8, like that. All right. Not the best drawing in the world, but I hope it does. So that means that if I count the number of molecules in energy level 0 and the number of molecules in energy level 8 at 5,000 degrees, okay, then what I'm going to note is that the number in level 8 is roughly 25% of the number in level 1. So we still have, or level 0. So we still have far more molecules in level 0, but the relative proportions are shifting to higher values as we increase the temperature. So that's what the Boltzmann distribution represents. And again, the importance of it is that that distribution of molecules has a significant impact on the thermodynamic properties of the system. And so and actually has an impact on the spectra that we get. Usually, for the vast majority of molecules that you looked at in organic chemistry when you were running IR spectra at room temperature, and again, we go back to 300 Kelvin here. All right, the vast majority of them are going to be in level 0. And in fact, this is 667 wave numbers. If we were looking at something over 3,000 wave numbers, like the carbon-hydrogen stretch or something like that, the relative amounts would be greater. There'd be far, far more molecules in level 0 than any other level. And that's actually key because if there were molecules populating the upper levels, if there were a lot of molecules populating the upper levels when you're running your spectrum, it would actually add more complexity to your spectrum because you'd have far more peaks in your spectrum, and that would just make things more difficult. So at room temperature, it's not something that for most types of vibrations we worry too much about, but if we increase the temperature, we're going to see it, and it is going to have an impact on thermodynamic properties. So that ends this very brief discussion of the Boltzmann distribution. We'll be doing some more stuff with calculations and talking more about the impact on various properties in the future. So stay tuned. We'll talk about it later.